At the very edge of absolute silence, 15 billion miles away, there is a solitary entity drifting through the eternal dark, guided by an electronic brain so primitive that it contains less memory than the smart key you use to start your car every morning. In November of 2023, this traveler suddenly began to emit a strange, digital scream, as if it were trying to whisper a final testament after nearly half a century of endurance. Scientists on Earth, wondering if this was the silent end of a legend or the beginning of an impossible rescue mission. Before we delve into this surgical operation, performed across 15 billion miles of void, please subscribe to join us as we journey toward the final limits of human knowledge. To understand why this solitary's breakdown felt so catastrophic in 2023, you first have to understand what kind of machine it actually is. Because the honest answer is one of the more quietly strange facts in the history of engineering. Voyager 1 is not a marvel of cutting-edge technology in the way we usually mean that phrase. It is, by every modern technical standard, a relic. Its central computers process roughly 8,000 instructions per second, which sounds reasonable until you consider that the smartphone in your pocket processes more than 14 billion instructions per second, making your phone approximately 1.7 million times more powerful than the most sophisticated spacecraft humanity has ever sent beyond the solar system. The entire onboard memory, everything Voyager 1 needs to store in order to function, navigate, collect data, and communicate across interstellar distances, amounts to 68 kilobytes total, which is less storage than a single low-resolution thumbnail photograph taken on a phone from 15 years ago. And yet this machine, with its greeting card-level computing power and its almost comically constrained memory, has continued operating through environments that destroyed every theoretical model built to describe them, through a radiation field that bombards its electronics with high-energy particles every second of every year, through temperature swings that would shatter most materials, across distances that reduce the sun itself to an unremarkable point of light. And it has done all of this for longer than most of the engineers currently working on it have been alive. The reason for this durability has almost nothing to do with computational sophistication, and almost everything to do with one quietly brilliant engineering decision. Made in the early 1970s, the choice of power source. Voyager 1 does not use solar panels. At the distance it now travels, so far from the sun that our star appears as nothing more than a bright dot among millions of others. Solar energy is essentially useless as a power source, and generating meaningful electricity from it would require panels larger than a football field. Panels that would be structurally impossible to deploy on a spacecraft, impossible to orient accurately across 47 years of travel, and impossible to protect from the micrometeorite impacts that would degrade them long before the mission reached any of its scientific objectives. Instead, the spacecraft draws its power from three devices called radioisotope thermoelectric generators, which is a technical name for something conceptually almost elegant. In its simplicity, take a material that generates heat as its atomic nuclei naturally decay. Surround that material with a device that converts the temperature difference between the hot radioactive core and the cold space environment into a flow of electrons, and you have a power source with no moving parts whatsoever, no fuel to combust, no mechanism to jam or corrode or wear against another mechanism, just the slow, patient, utterly reliable transformation of plutonium into heat, into electricity, into signal, year after year, decade after decade. The specific material is plutonium-238, chosen with considerable deliberation over other radioactive isotopes for reasons that go beyond the obvious. Plutonium-238 has a half-life of 87.7 years, long enough that the decay rate remains useful across a multi-decade mission, but short enough that the heat output is substantial rather than negligible. More importantly, for an instrument-carrying spacecraft, it decays almost exclusively by emitting alpha particles, which are the most easily shielded form of radiation. A thin layer of material stops them completely, meaning the spacecraft's delicate scientific instruments, positioned meters away from the generators, are exposed to almost none of the radiation that powers them. This combination of properties makes plutonium-238 essentially the ideal fuel for a deep space mission in a way that no other readily available radioactive material matches. When Voyager 1 launched in September of 1977, its 3 generators together produced around 470 watts of electrical power, roughly enough to run 4 conventional incandescent light bulbs simultaneously. Today, after 47 years of continuous operation, those same generators still produce more than 200 watts. Because the mathematics of plutonium's slow decay work in the spacecraft's favor, losing approximately 0.8% of output per year means losing roughly 4 watts annually, the equivalent of 1 LED light bulb going permanently dark every 12 months while the remaining lights stay on. The power budget is shrinking, and the engineering team has had to make increasingly painful choices about which instruments to keep alive and which to power down. But the fundamental energy source continues, patient and inexorable, just as it has since the spacecraft left the launch pad. The brilliance of this design becomes even clearer when you consider what it replaced. Earlier, deep space probes used solar panels, which worked fine in the inner solar system but became useless beyond the orbit of Mars. Other options, chemical batteries, fuel cells, would have been exhausted within years. The plutonium generators have a design life measured in decades, and an actual operational life that has now extended to nearly 5 decades, with no fundamental failure of the power-generating mechanism itself. In the history of engineering, it is difficult to think of another design choice at the component level that has had a larger effect on what a single mission was ultimately able to accomplish. The rest of the spacecraft was designed around the same principle of deliberate minimalism. The recognition that, in an environment where nothing can be serviced, replaced, or repaired, complexity is the enemy, and simplicity is the closest thing available to immortality. Navigation relies on gyroscopes and star trackers that orient the spacecraft by referencing known stellar positions, a method so fundamentally grounded in physics that it requires no software updates, no connectivity to external systems, no recalibration beyond the occasional small thruster burn, just the unchanging geometry of stars that have occupied the same relative positions for millions of years and will continue to do so for millions more. The main antenna, a dish 3.7 meters across, roughly the span of a small car's length, points permanently toward Earth, adjusted only by the most miserly thruster firings imaginable, consuming fuel at a rate so slow that the spacecraft's remaining propellant supply is still being managed carefully decades after launch. What this philosophy produced was a machine designed to be wrong about as few things as possible, rather than a machine designed to be capable of as many things as possible. And in the context of a multi-decade deep space mission, that turned out to be the correct trade-off. For 46 years, that philosophy held without a single fundamental failure. The signal arrived, the data streamed, the instruments measured, and the spacecraft moved steadily outward at roughly 17 kilometers per second, fast enough that if it were traveling horizontally across the surface of the Earth, it would cross the width of the continental United States in roughly 4 minutes. And then, on the 14th of November, 2023, the data stream was replaced by gibberish, and the philosophy was put to its hardest test yet. But before we get to the breakdown and what the repair reveals about what this machine means to us, there is a more fundamental question worth spending time with. How did a spacecraft designed for a 5-year mission end up in interstellar space at all? And what sequence of decisions, in calculations, and extraordinary good fortune made it possible. The existence of Voyager 1 as an interstellar spacecraft rather than a piece of space debris orbiting somewhere between Jupiter and Saturn depends on a calculation performed by a graduate student during a summer internship in 1964, using a mechanical calculator and a set of celestial charts in an era before digital computers were widely available in research settings. His name was Gary Flandreau, and the problem he had been assigned was deceptively simple. In its framing, determined the most energy-efficient trajectories from Earth to the outer planets. What he found, working through thousands of individual orbital calculations over weeks of painstaking arithmetic, was something that the planetary science community had not fully appreciated before he wrote it down. A rare geometrical alignment of Jupiter, Saturn, Uranus, and Neptune, all four of the outer gas giants, positioned on the same side of the solar system in a configuration that would allow a spacecraft launched at precisely the right time to visit all four of them in a single journey, not by burning enormous amounts of fuel to travel between them, but by borrowing gravitational energy from each planet in turn, using each world's own mass as a kind of cosmic slingshot to accelerate toward the next destination. The technique Flandreau recognized as applicable here is called a gravity assist, and it is one of those ideas that sounds counterintuitive until you work through the physics carefully, at which point it reveals itself to be not just possible, but inevitable given Newton's laws. When a spacecraft passes close to a massive planet, the planet's gravitational field pulls the craft into a curved path, accelerating it as it approaches, and then, because the spacecraft's speed relative to the Sun includes the planet's own orbital velocity as a component, releasing it on a new trajectory carrying more kinetic energy than it arrived with, the planet loses an infinitesimally small fraction of its own orbital momentum in the transaction. So small that measuring the effect on Jupiter's orbit from every gravity to assist humanity has ever performed would require instruments that do not yet exist, while the spacecraft gains free speed that would otherwise require enormous quantities of rocket fuel to achieve. What made Flandreau's finding extraordinary was not the technique itself, which had been described theoretically, but the timing, the alignment he had identified was a rare event, occurring once every 175 to 176 years, and the window for launching to take advantage of it was open only between 1976 and 1979. The arithmetic of orbital mechanics is unforgiving in its precision. Miss the window by a year in either direction, and the geometry of the alignment degrades to the point where the multi-planet trajectory becomes impractical. Miss it entirely, and the next opportunity arrives sometime in the 2150s, when everyone involved in the 1970s mission will have been dust for more than a generation. Flandreau's calculation revealed something else that changed the entire calculus of outer solar system exploration with the gravity assist chain. The travel time to Neptune, the outermost gas giant, which would normally require a direct flight of roughly 40 years given the propulsion technology available in the 1970s, could be compressed to under 12 years. The difference between a 40-year mission and a 12-year mission is not merely a matter of patience. It is the difference between a mission that requires essentially perpetual institutional commitment across multiple generations of engineers and scientists, and one that a single career generation can see from beginning to end. Flandreau brought his findings to senior scientists at JPL, and the initial reception was, by his own account, underwhelming. The obstacles seemed too numerous, the timescales too uncertain, the list of things that could go catastrophically wrong too long to make the endeavor feel like a reasonable institutional commitment. A mission designed to last 12 years on hardware that had never been tested beyond 5 years, traversing radiation environments that had never been directly measured, navigating trajectories that depended on gravitational interactions with planets whose atmospheric and magnetic properties were only approximately understood. It was a lot to ask. What eventually resulted from years of political and budgetary negotiation was a scaled-down version of the original Grand Tour Concept 2 spacecraft instead of one. Because redundancy is the closest thing to insurance that interplanetary exploration has available. Launched 16 days apart in the fall of 1977 from Cape Canaveral, Voyager 2 went first. On the 20th of August, on the slower trajectory that would allow it to visit all 4 outer planets, Voyager 1 followed on the 5th of September, on a faster path that would reach Jupiter and Saturn sooner but sacrifice the Uranus and Neptune visits in exchange for the ability to make a close approach to Saturn's moon Titan, which the scientific community considered a higher priority than the 2 outer planets. Within 2 years of launch, Voyager 1 had overtaken its older sibling entirely. The faster trajectory, compressing the travel time to Jupiter to less than 2 years, and by 1980, it had completed all of its planned planetary encounters and begun the long, unguided coast toward the edge of the solar system and beyond. All of this because a graduate student did the arithmetic carefully enough. In the summer of 1964, to notice a window that had been sitting in the mathematics of planetary motion since those planets first formed, waiting for someone with a mechanical calculator and enough patience to find it. When that window closes again, which it already has, the next generation of humans who want to send a spacecraft through the outer solar system on a grand tour trajectory will be doing the math in a world that will be as different from ours as ours is from the world of 1964. What they will be launching, if they launch anything, will carry instruments we cannot currently design, powered by energy sources we have not yet developed, toward a set of scientific questions that Voyager 1 itself will have raised and left unanswered. Questions that nobody in 1964 could have imagined asking, because nobody in 1964 knew what Voyager 1 would find when it arrived. The scientists who designed Voyager 1's instruments had access to the best available knowledge of the outer solar system in the early 1970s. Decades of careful, telescopic observation, the theoretical frameworks of planetary science developed since the 1930s, and the preliminary data returned by Pioneer 10 and 11, which had performed the first flybys of Jupiter and Saturn respectively. Their expectations were reasonable, well grounded in established science, and almost systematically wrong. The first shock arrived at Jupiter's moon Io. Io is one of Jupiter's 4 large Galilean moons, large enough to be a planetary body in its own right, roughly the same size as Earth's moon. And every theoretical model of planetary geology available before Voyager 1's arrival predicted that it would look essentially identical to our moon, ancient, cold, heavily cratered from billions of years of meteorite impacts, geologically inert, a world whose interesting volcanic and tectonic history had ended long before any instrument was available to record it. The reasoning was sound and followed directly from established physics. Small rocky bodies have limited internal heat, and without internal heat to drive volcanic activity and tectonic movement, the surface simply accumulates impact craters over time, preserving a record of the early solar system's bombardment history like an unretouched archaeological site. Every rocky moon in the outer solar system was expected to display this pattern, and there was no compelling reason to think Io would be different. On the 8th of March, 1979, 3 days after Voyager 1 completed its closest approach to Jupiter, a navigation engineer named Linda Morabito was processing images of Io as part of the routine process of refining the spacecraft's positional data, a task that required comparing the apparent positions of moons against their predicted positions to calculate the spacecraft's exact trajectory. While examining one of these images, she noticed a curved shape extending from the edge of Io's disk, a shape that resembled an umbrella or a crescent. roughly 300 kilometers tall, rising above the moon's limb against the blackness of space. Her immediate assumption was that it might be another of Jupiter's smaller moons, partially obscured by Io, creating an artifact in the image that looked like a feature on Io's surface. It was the most parsimonious explanation available, and it was wrong. What Morabito had found was the first active extraterrestrial volcano ever observed, a plume of sulfur and sulfur dioxide erupting from a vent on Io's surface, with enough force to propel material 500 kilometers above the customate in surface, at temperatures exceeding 1300 degrees Celsius, hotter than any volcanic eruption on Earth, and at a rate that would have been completely undetectable to any telescope then in existence, because the column was visible only as a silhouette against the emptiness of space, not against the planet's surface. Over the course of Voyager 1's flyby, the cameras identified 9 separate active volcanic eruptions on Io, 9 simultaneous plumes, each one in a slightly different stage of its eruptive cycle, transforming a world that was supposed to be among the most geologically dead in the solar system into the most volcanically active world that anyone had ever observed. The physical explanation, which required years to fully develop, centers on a phenomenon called tidal flexing. Io orbits Jupiter at a distance close enough that Jupiter's enormous gravitational field, combined with the gravitational tugs of the other large Galilean moons, which pull Io's orbit into a slightly irregular ellipse, continuously squeezes and stretches the moon's interior as it orbits, the way you might repeatedly bend a metal paperclip back and forth, generating heat through internal friction. That heat has nowhere to go except outward through the surface, driving the volcanic activity that continually resurfaces the moon and obliterating every impact crater almost as soon as it forms, which is why Io's surface shows almost no craters at all. Its geological clock reset every few thousand years by new lava flows. The discovery that tidal heating could maintain geological activity in a body as small as Io, regardless of its initial heat budget, fundamentally changed how planetary scientists think about where in the solar system, and by extension, where in the universe, the conditions necessary for geological activity, liquid water, and potentially life might exist. Saturn brought a different kind of surprise, one that has remained only partially explained for more than 4 decades since its discovery. By the time Voyager 1 arrived at Saturn in November of 1980, the rings were among the most studied features in the solar system outside of the planets themselves. Their structure, divided into several broad bands, separated by gaps associated with gravitational resonances with Saturn's moons, had been mapped telescopically to the best resolution available, and the prevailing theoretical framework described their behavior in terms of orbital mechanics that had been understood since Kepler particles close to Saturn orbit faster than particles farther out, and the differential in orbital speeds creates the smooth, predictable structure of each ring band. On the 6th of October, 1980, while Voyager 1 was still 50 million kilometers from Saturn, a distance roughly 1/3 of the separation between Earth and the Sun, scientists analyzing the incoming images noticed features in the B ring that violated this framework in a way that seemed impossible given the prevailing model. Dark radial streaks extended outward from the inner edge of the ring, like the spokes of a wheel, crossing the ring bands at angles inconsistent with orbital mechanics, and rotating at a speed that tracked Saturn's magnetic field rather than the orbital periods of the particles they appeared to overlay. In a gravitational system, the inner parts of a ring rotate faster than the outer parts, always, without exception, because that is what orbital mechanics requires. The spokes were rotating as a unit, maintaining their radial shape across the width of the ring, which meant that something other than gravity was maintaining their structure. The leading explanation, Developed over decades of subsequent research and partially supported by observations from the Cassini spacecraft that orbited Saturn from 2004 to 2017, involves the behavior of very fine dust particles in Saturn's ring system when they acquire an electric charge through interactions with the planet's magnetic field and the energetic particles trapped in its radiation belts. Charged particles respond to magnetic fields as well as to gravity, and in the region of the B ring, the balance between magnetic force and gravitational force can, under the right conditions, allow fine charged particles to lift slightly above the main ring plane and remain suspended in a configuration that co-rotates with Saturn's magnetic field rather than with the orbital mechanics of the larger ring particles. Below them, the spokes on this model are composed of these suspended charged dust grains, temporarily lifted and then falling back into the ring over timescales of hours to days. What makes this explanation both compelling and unsatisfying is that after more than 4 decades and 2 major spacecraft missions, the conditions that trigger spoke formation, why they appear at some longitudes and not others, why they are more prominent at certain phases of Saturn's rotation, how they form so rapidly that they can develop within a single orbital period, remain subjects of active scientific debate. A feature of Saturn's rings was discovered in 1980 and is still imperfectly understood today, which is either a frustrating loose end or a testament to the inexhaustible complexity of a solar system that has been studied continuously for 4 centuries without running out of new things to reveal, depending on your disposition. Saturn, Saturn's largest moon and the 3rd major target of Voyager 1's flyby campaign, produced a different kind of result, one measured not in what was discovered but in what was sacrificed. Titan had been known since the 1940s to possess an atmosphere, making it the only moon in the solar system confirmed to have one. And the composition of that atmosphere, nitrogen-rich, laced with organic compounds, made it one of the most scientifically compelling bodies in the outer solar system. A potential analogue for the early Earth before life altered the planet's chemistry. The opportunity to fly close to Titan and characterize its atmosphere in detail was considered, by many members of the scientific team, to be more valuable than any other single observation Voyager 1 could make. The engineering cost of that opportunity was Voyager 1's future as a planetary explorer. Using Titan's gravity to achieve the necessary close approach would deflect the spacecraft's trajectory sharply out of the plane of the solar system, tilting it above the ecliptic, the flat disk in which the planets orbit, in a direction that would never bring it close to another planet again. Every other planetary body in the solar system would become permanently unreachable. Pluto, then still classified as a planet, would receive no Voyager visit. Neither would Uranus or Neptune. Those would fall to Voyager 2. The Titan flyby was a one-way commitment. NASA chose Titan. On the 12th of November, 1980, Voyager 1 passed within 6,000 kilometers of Titan's surface, closer than any human-made object had ever approached the Moon, and the cameras looked down at a world wrapped in a dense, featureless orange haze, so thick and so uniform that it was effectively opaque to every wavelength the instruments were capable of measuring. The atmospheric data was rich and scientifically valuable. The surface images were, effectively, a wall. Titan had received the sacrifice Voyager 1 made for it and given back chemistry in return. Its surface would remain hidden until the Cassini-Huygens mission delivered a probe through that orange curtain in 2005, 24 years after Voyager 1's flyby, to reveal a landscape of methane lakes, hydrocarbon dunes, and river channels carved by liquid that is cold enough to dissolve rock. Voyager 1, having paid its price, turned its course outward. No more planets to visit. No more gravity assists to perform. Nothing ahead but the long, quiet coast toward whatever lay beyond the edge of the solar system. which at that point in 1980 nobody had ever directly observed from inside it. Before Voyager 1 crossed into interstellar space, before it discovered the plasma hum of the medium between the stars, before its memory chip failed and its engineers worked miracles of remote diagnosis across 15 billion miles, it carried something that has nothing to do with orbital mechanics or plasma physics. Something that sits on its outer hull inside a protective aluminum cover, waiting for a recipient that will almost certainly never come. The Golden Record, a 12-inch gold-plated copper disc, is one of the stranger objects ever launched into space, and the process by which it was assembled reflects something that the official mission documentation does not fully capture: the understanding, held by at least some of the people involved, that Voyager 1 was not merely a scientific instrument but a representation of human civilization at a particular moment in its development, sent outward at a time when it was genuinely uncertain whether any other spacecraft would ever follow it this far. The record contains 115 images encoded as audio signals. Images spanning human anatomy, mathematics, comparative scale, terrestrial geography, the structure of DNA, and the daily texture of human life across dozens of cultures. It contains 12 minutes of natural sounds: surf breaking on a beach, wind moving through trees, thunder, rain, the calls of birds and insects, the songs of humpback whales, the sound of a human footstep on gravel, the first cry of a newborn. It contains 90 minutes of music selected to represent the full range of what humans have made with rhythm and melody and silence. From a Javanese court gamelan to a pygmy girl's initiation song to a Bach Brandenburg concerto performed on a pipe organ, from Louis Armstrong's melancholy blues to a Navajo night chant to a piece of music from Georgia in the Caucasus that its composers had no reason to believe would ever travel beyond the borders of their country. It contains greetings in 55 languages, among them Ancient Akkadian, a language whose last native speakers died more than 2,000 years ago, a language that exists now only in clay tablets and scholarly transcription. And it contains the electrical brain activity compressed into a 1-minute audio sequence of a woman named Anne Druyan, recorded 2 days after she and Carl Sagan had acknowledged to each other that they were in love, while she sat and tried to think about what it meant to be a conscious creature in a universe that appears largely indifferent to consciousness. Druyan later described what she was thinking during the recording as a kind of compressed summary of human history and human feeling, the arc of ideas from the earliest stone tools to the spacecraft that was about to carry her thoughts into space. The experience of love as a specific and identifiable neurological state, the sense of being temporarily and improbably alive in a cosmos whose age and scale dwarf everything she could directly perceive. The recorded brainwaves, she said, sound when played back like a continuous string of fireworks. Adense, rapid, irregular sequence of electrical pulses that carries, embedded somewhere in its pattern, whatever the experience of being human feels like from the inside on a day when everything seems to matter. Carl Sagan wanted the Beatles' song Here Comes the Sun on the record. The Beatles themselves wanted it included. George Harrison, by several accounts, was enthusiastic about the idea. Which held the copyright, declined on commercial grounds, which means that the most carefully curated document of human civilization and feeling ever assembled was successfully blocked from including one of the most beloved pieces of music from the century in which it was made by a standard issue licensing dispute. A detail that is simultaneously absurd, deeply characteristic of our species, and somehow reassuring in its demonstration that even the grandest human projects are assembled in the same world where ordinary commercial friction applies. Etched into the cover of the record, alongside instructions for playing it, is a diagram of 14 pulsars, rapidly rotating neutron stars whose precise rotation rates are as unique and stable as fingerprints, varying from pulsar to pulsar in ways that cannot be duplicated by any other astrophysical phenomenon. Arranged as a map that triangulates the position of our Sun relative to the center of the galaxy and relative to each other, providing any recipient with the means to locate our star in the three-dimensional structure of the Milky Way. It is a return address placed on the outside of a spacecraft whose mission had nothing to do with being found, addressed to recipients whose existence is unconfirmed, whose location is entirely unknown, and whose ability to interpret the diagram depends on a prior knowledge of pulsar physics that cannot be taken for granted. The probability that the golden record will ever be found and understood by an extraterrestrial intelligence is, by any honest astronomical calculation, extraordinarily small, not zero, because the spacecraft will continue to exist for as long as the galaxy continues to exist, but small enough that designing the record around the assumption of its eventual discovery was an act of conscious optimism rather than practical planning. There is something worth dwelling on in the structure of the golden record's contents, in the decision to include not only the polished achievements of human civilization but also its raw biological reality, the sound of a pulsar, yes, and a Bach fugue, yes, but also the sound of a human kiss, the sound of a mother soothing a child, the electrical noise of a nervous system processing the experience of being in love. The record was not designed to present humanity at its most impressive or its most rational. It was designed to present humanity as it actually is, a species that builds spacecraft and also falls in love, that understands orbital mechanics and also writes music for instruments made of stretched animal skin, that can calculate the trajectory of a spacecraft to the edge of the solar system, and also weeps at the sound of a whale singing in an ocean it will never see again. Whatever intelligence eventually finds the record, if any does, across whatever impossible span of time, will receive not a resume, but something closer to a portrait. Assembled in 6 weeks by a committee of humans who understood they were working on a deadline that the universe would not extend, 10 years after Voyager 1's launch, with the planetary encounters complete and the spacecraft now heading outward on its solitary coast, Carl Sagan made one final request of the mission team: turn the cameras around, point them back at the solar system, at the Sun and its family of planets, and take one last portrait before the distance becomes too great for the cameras to serve any further scientific purpose. The mission team agreed. On the 14th of February, 1990, Voyager 1 turned its camera toward home and took 60 individual frames showing the solar system from a distance of more than 6 billion kilometers. Earth appears in one of those frames as a fraction of a single pixel, a pale blue dot, less than 1/12 of a pixel across, barely distinguishable from the scattered light refracting through the camera's optics. Suspended in a beam of sunlight, like a mote of dust caught in light coming through a window, the image shows no continents, no oceans, no clouds, no cities. Nothing that would indicate to any observer, without prior knowledge, that the pixel contains every human being who has ever lived, every war ever fought, every piece of music ever composed, every idea ever thought, every moment of love or grief or wonder that has ever been experienced by a conscious creature on this particular piece of rock. 34 minutes after the last frame was captured, at 5:22 in the morning, Greenwich Mean Time, Voyager 1's cameras were shut down permanently, not because they had failed, but because the power they consumed was needed for the instruments that could still do useful scientific work in the void ahead, where there would be nothing to photograph but empty space and the invisible structure of a medium that the cameras could not see regardless of how long they pointed into it. Voyager 1 has traveled blind ever since, measuring a universe it can no longer look at, sending home data it cannot see, carrying its record player and its map of pulsars and its brainwave recording into the dark. For most of the history of planetary science, the outer boundary of the solar system was defined by convention rather than physics, placed at the orbit of the outermost known planet, adjusted outward whenever a new body was discovered. A conceptual line drawn wherever it was convenient to draw it rather than wherever a physical phenomenon created an actual demarcation. The assumption underlying this convention was that the transition from solar system to interstellar space was probably gradual and probably unremarkable. A slow thinning of solar influence, a gradual thickening of interstellar material, a frontier that blurred rather than broke. What Voyager 1 found was that the boundary is real. It is physical. It produces measurable and dramatic changes in every quantity the spacecraft's instruments could detect. And it is almost nothing like what the models had described. The Sun continuously emits a stream of charged particles, electrons, protons, and heavier ions, in all directions simultaneously, at speeds between 400 and 800 kilometers per second. A continuous outflow called the solar wind that carries the Sun's magnetic field with it and inflates an enormous bubble of solar influence in the surrounding interstellar medium. A bubble called the Heliosphere that contains every planet, every moon, every asteroid, and every human being in the solar system within its boundaries. This bubble is not infinite at some distance from the Sun. The solar wind's pressure equals the pressure of the interstellar medium pushing back against it, and the wind stalls, first slowing from supersonic to subsonic speeds in a shock wave called the termination shock, then turbulently mixing with interstellar material in a zone called the heliosheath, and finally stopping altogether at a boundary called the heliopause, where solar particles give way definitively to interstellar ones. The models of heliospheric structure available before Voyager 1's outer crossing placed the termination shock at approximately 85 astronomical units from the Sun, where 1 astronomical unit equals the Earth-Sun distance of approximately 150 million kilometers, making 85 of them a distance roughly equivalent to traveling from Earth to Saturn and continuing outward for nearly twice Saturn's orbital distance again. In December of 2004, Voyager 1 crossed the termination shock, and it was at 94 astronomical units, not 85. The boundary was displaced by roughly 800 million miles from where the models had placed it, a miss equivalent to placing the entire orbit of Saturn at the wrong distance from the Sun, and a miss that forced a systematic review of the assumptions underlying the heliospheric model rather than simply a parameter adjustment within it. More disorienting than the position of the termination shock was the character of the region beyond it, the heliosheath. The zone between the termination shock and the heliopause turned out to be far more turbulent, far more dynamic, and far more asymmetric than theoretical models had anticipated, with the solar wind behaving differently in different directions, and the magnetic field fluctuating in ways that suggested the heliosphere's outer boundary was being pushed and pulled by structures in the interstellar medium that the models had not incorporated. The simple picture of a smooth, spherical bubble inflated by the solar wind against a uniform interstellar pressure gave way to something considerably messier. A bubble that is compressed on the side facing the direction of the solar system's motion through the galaxy, elongated on the opposite side, and peppered with discontinuities and turbulent regions that the pre-Voyager models had no category to describe. The heliopause crossing in August of 2012 produced its own set of contradictions. When Voyager 1 passed through what appeared to be the outermost boundary, identified by an abrupt change in the energetic particle count from predominantly solar to predominantly galactic, the magnetic field measurement told a different story, showing a field direction more consistent with the solar wind than with the interstellar medium. as though the spacecraft had crossed through one layer of the boundary but not another. The data from the two instruments was internally inconsistent in a way that no single pre-existing model could accommodate, and resolving the inconsistency required waiting for a solar eruption that launched a plasma wave in March of 2012. A wave that traveled outward at solar wind speeds for over a year and finally reached Voyager 1's position in April of 2013, causing the surrounding plasma to oscillate at a frequency that functioned as a direct density measurement, confirming that the electron density around the spacecraft was 40 times higher than anything inside the heliosphere, and definitively establishing that Voyager 1 was in interstellar space by the most unambiguous measurement available. Even if the boundary it had crossed turned out to be a region of gradual transition rather than a sharp line, the picture that emerged from combining all of these measurements, the unexpected distance of the termination shock, the turbulent heliosheath, the ambiguous magnetic field at the heliopause, the density jump confirmed by plasma oscillation, was one of a solar system boundary that is far more complex, far more dynamic, and far more structurally rich than anyone had imagined. A frontier that blurs rather than breaks, layered rather than sharp. Its exact location depending on which physical quantity you choose to measure, and arguably not fixed in the same position for any two such quantities simultaneously. This is what the edge of home actually looks like, at the resolution that only direct measurement can provide. After the cameras were turned off and the planets fell far behind, Voyager 1's scientific work did not end. It changed character entirely, shifting from the exploration of known objects whose existence had been confirmed by telescope to the direct measurement of an environment whose properties had been modeled theoretically but never sampled in situ. The interstellar medium, the material filling the space between the stars, was supposed to be the simplest possible environment for the spacecraft to move through: diffuse, quiet, approximately uniform, presenting no dramatic gradients or boundaries or structures that would challenge or complicate the instruments. The interstellar medium turned out to be none of those things. In 2021, a research team at Cornell University published findings based on data from Voyager 1's plasma wave instrument, a device that measures oscillations in the electron density of the medium surrounding the spacecraft by detecting the electromagnetic waves those oscillations produce, that revealed something the instrument's designers had not anticipated finding. Between the discrete bursts of plasma wave activity triggered by solar events, which had been observed and studied since the spacecraft's crossing of the heliopause, the instrument was detecting a continuous, low-level, steady oscillation at around 2.6 kHz, a frequency within the range of human hearing, roughly the pitch of a person whistling a relatively high note, that persisted regardless of solar activity, regardless of seasonal variations in the solar wind, regardless of anything happening on the Sun or in the inner solar system. The interstellar medium through which Voyager 1 was traveling was humming to itself at a constant pitch, the plasma vibrating at its own natural frequency, the way a column of air in a pipe vibrates at a frequency determined by its length and composition. The researchers described the sound as resembling gentle, steady rain, a smooth, continuous background tone with none of the dramatic variations that characterized the plasma activity associated with solar events. Shami Chatterjee, a Cornell astronomer who worked on the analysis, framed the significance of the finding in terms that illuminate why it matters beyond its evocative quality for the first time. He noted, the spacecraft was providing continuous, real-time measurement of the plasma density of the interstellar medium without needing to wait for a solar event to create a measurable disturbance in it. Voyager 1 was effectively taking the pulse of interstellar space on a continuous basis, not just during moments when the Sun happened to send a wave through the medium it was traveling in. What that continuous measurement revealed was that the local interstellar medium is not the uniform, static environment that theoretical models had generally assumed it to be. The plasma density measured by Voyager 1's instruments had been increasing steadily since the spacecraft crossed the heliopause in 2012, reaching levels roughly 40 times higher than anything recorded inside the Heliosphere. By the time the 2021 paper was published, and the trend showed no sign of leveling off, suggesting that the spacecraft was moving through a region of the local interstellar medium with a genuine density gradient, a region where the material between the stars is getting progressively denser rather than remaining constant. This finding contradicted the standard model of the local interstellar medium as an approximately homogeneous, low-density plasma cloud, implying instead that the region immediately outside our heliosphere has significant internal structure, density variations, possibly flows or concentration gradients associated with the large-scale structure of the interstellar material that surrounds us. The density information also allowed researchers to refine their understanding of the three-dimensional shape and size of the heliosphere itself, because the pressure balance that determines where the heliopause sits depends on the density of the interstellar medium pushing against it. And a denser interstellar medium means a more compressed heliosphere. Every measurement Voyager 1 makes of the interstellar plasma density is, in this sense, also a measurement of the environment that shapes the bubble of solar influence, within which all of human experience has taken place. This is the quality that makes Voyager 1's interstellar data irreplaceable. It is not modeling, not inference, not theoretical prediction, but direct contact with the actual medium. The spacecraft physically moving through the plasma and measuring its properties with instruments that cannot be fooled by assumptions built into a theoretical framework. No telescope on Earth or in orbit around Earth can replicate this, because telescopes measure the light that passes through the interstellar medium, not the medium itself. The way you can learn something about a river by watching a leaf float on its surface. But you learn something fundamentally different by putting your hand in the water and feeling the current push against it. Voyager 1 has its hand in the water, and the current is stronger and more structured and more directional than the models built from watching the leaf said it would be. And touching it, the spacecraft keeps finding that it is not what the models said it was. More structured, more varied, more full of gradients and flows and density differences than the smooth, quiet void of theoretical prediction. The universe between the stars has texture, and Voyager 1 is the only instrument that has ever been close enough to feel it. On the 14th of November, 2023, at 5:45 in the morning Pacific time, engineers at NASA's Jet Propulsion Laboratory noticed that Voyager 1 had stopped sending readable data. The carrier signal was present. The spacecraft was transmitting. The Deep Space Network's 70-meter antennas were receiving. The radio link across 15 billion miles was intact. But the data that was arriving was not the telemetry stream the instruments should have been generating. Instead, the signal carried a repeating binary pattern, a cycling sequence of ones and zeros that looped without variation, carrying no scientific data, reporting no instrument readings, encoding nothing that anyone on the receiving end could decode as meaningful information. The spacecraft was not silent. It was talking, loudly and clearly, in a language that appeared to have lost all its grammar. The engineering team's first challenge was not diagnostic, but logistical. Every interaction with Voyager 1 operates on a 45-hour round-trip delay, which means that the minimum time between sending a command and receiving a response is 45 hours, nearly 2 full days. Diagnosing a hardware or software problem under these conditions is a fundamentally different kind of engineering challenge than anything that can be practiced on Earth, where real-time feedback allows rapid iteration and the consequences of a wrong command can usually be undone within seconds. At Voyager, distances, Every command has to be formulated with enough care and precision that the team is willing to commit to its consequences before knowing what those consequences are. And the wrong command can disable systems that cannot be re-enabled from the ground. The team working on the problem was operating with additional constraints that compounded the difficulty. Voyager 1 was designed in the early 1970s and runs software written in assembly language, a low-level programming language that was largely superseded by higher-level languages in the 1980s, and that very few practicing engineers today have working knowledge of, unlike modern spacecraft, for which ground-based software simulators can model the spacecraft's behavior in real time, allowing engineers to test commands before sending them. Voyager has no functional simulator because the cost of building and maintaining one was never considered justified for a mission that was originally designed to last 5 years. Much of the original design documentation exists on paper rather than in any digital format, and some of it has never been fully transcribed. The engineers who wrote the original flight software, who understood from first principles how every subsystem interacted with every other subsystem, had retired decades earlier. Some had died. The institutional knowledge of the spacecraft's behavior under edge conditions had to be reconstructed from whatever remained. By March of 2024, 4 months after the breakdown began, the team had developed a plan to diagnose the problem directly. They sent a command instructing the flight data system, which is the component responsible for packaging and formatting scientific and engineering data for transmission, to read out its entire memory and return the contents to Earth. This was a known procedure, rarely used, that would produce a direct inventory of every value stored in the flight data system's memory. And if something in that memory had changed unexpectedly, the inventory would reveal both what had changed and where. The response, when it arrived 45 hours later, confirmed what the team had suspected but not yet proven. A single chip within the flight data system, one component among the thousands that constitute the spacecraft's electronic infrastructure, had failed. The chip stored approximately 3% of the flight data system's total memory, roughly 2 kilobytes out of 68. But those 2 kilobytes contained code that was critical to the process of formatting data for transmission. The failure had corrupted that code, and the corrupted code was causing the flight data system to output the repeating nonsense pattern instead of the scientific telemetry. The instruments were continuously generating. The cause was almost certainly one of two things, and the team had no way to determine which. Either the chip's semiconductor material had degraded through natural radioactive processes over 46 years of continuous operation, its crystalline structure slowly accumulating damage until it could no longer reliably store information, or a high-energy cosmic ray, the kind of energetic particle that streams through interstellar space from every direction, carrying energies millions of times higher than anything produced in a terrestrial particle accelerator, had passed through the chip and scattered enough energy to permanently alter the state of the memory cells it hit. Both mechanisms are real. Both operate continuously on any semiconductor device in space, and at 46 years of exposure. Either is entirely plausible. Distinguishing between them after the fact would require tests that could not be performed remotely on a spacecraft 15 billion miles away. What mattered, from a practical standpoint, was not the cause but the solution. And the solution was constrained by the same 68 kilobyte total memory budget that had shaped every other engineering decision made about the spacecraft since launch. The corrupted code could not simply be deleted and rewritten from scratch. The failure was in the storage medium itself, not in the data it contained, meaning that any code written to the failed chip would be just as corrupted as the code it replaced. The solution was relocation. Move the affected code to parts of the flight data system's memory that were still functional, and rewrite the pointers that told the rest of the software where to find each piece of code to reflect the new locations. The problem with this approach was spatial, No single available section of the working memory was large enough to contain the entire affected code block. The team had to divide the code into segments, distribute those segments across multiple different memory locations, and ensure that all the connections between segments, the internal references and function calls that allowed the code to execute as a coherent program, were updated to reflect the new geography of the software across the memory space. This required a precise understanding of the flight data system's architecture, of every dependency between code segments, of every assumption built into the original software about where each piece of code lived in memory. Before the segments could be relocated, space had to be created for them, which meant deciding what to delete from the working memory to free up the necessary addresses. The team identified blocks of code that were no longer operationally necessary, and among them, archived and untouched in the flight data system's memory for more than 4 decades, was the software associated with the Jupiter flyby of 1979. Code written when the spacecraft was still in the inner solar system. Code designed to manage data collection during a planetary encounter that had ended 44 years earlier. Code that had waited in Voyager 1's memory through the entire subsequent history of the mission. Through the Saturn flyby, through the Heliosphere crossing, through the heliopause, through the plasma hum discovery, and that was now deleted to make room for the repair that would keep the spacecraft alive a few years longer. On the 18th of April, 2024, the first segment of relocated code was transmitted to Voyager 1. 22.5 hours later, the signal arrived at the spacecraft. 22.5 hours after that, the response arrived at Pasadena on the 20th of April, 45 hours after the first repair command was sent. Voyager 1 began transmitting readable engineering telemetry for the first time in 5 months, its systems reporting their status in coherent data for the first time since November. The team members gathered in the conference room at JPL, celebrated in the specific way that people celebrate after months of uncertainty, resolved in 45-hour increments, with the kind of relief that has been accumulating since the moment the data stream went silent and is finally, abruptly, allowed to discharge. By the 22nd of May, 2 of the 4 scientific instruments had been restored to normal data collection. By the 13th of June, all 4 were operational. Voyager 1 was returning coherent scientific data from interstellar space. Its instruments measuring the plasma hum and the cosmic ray flux and the magnetic field of the medium between the stars. As though the 5-month interruption had been a pause in a conversation rather than a near-death experience on a spacecraft that cannot be resuscitated twice. Then, in October of 2024, a fault protection system triggered unexpectedly after engineers activated a heater on one of the spacecraft's subsystems, and the primary X-band radio transmitter, the main communication channel for scientific and engineering data, shut itself down automatically. The team spent weeks searching for and amplifying a backup signal, diagnosing the fault condition, and eventually restoring the primary transmitter to operation, adding another chapter to a repair history that was beginning to resemble not an engineering project, but something closer to medical maintenance of an elderly patient whose every organ is still functioning, but none of them with the margins of safety they had when they were new. In May of 2025, as a postscript to this sequence of recoveries, the team succeeded in restoring the backup roll thrusters, the devices that control the spacecraft's rotational orientation, that had last been used in 2004 and had been considered essentially beyond recovery due to the age and condition of their fuel lines and control valves. Their restoration extends the operational lifetime of the spacecraft's attitude control system, which is what keeps the antenna pointed at Earth and the instruments pointed at the interstellar medium, and buys additional months or years of scientific operation before the declining power budget forces the next hard choice about which system to sacrifice for the sake of the others. On the 25th of February, 2025, NASA powered down the cosmic ray subsystem instrument aboard Voyager 1, one of the 4 scientific instruments restored during the previous year's repair campaign. The shutdown was not triggered by a failure. The instrument was working. It was shut down because the spacecraft's total electrical budget, declining at roughly 4 watts per year as the plutonium in its generators continues to decay, had reached the point where keeping all 4 instruments powered simultaneously was consuming electricity that the engineering team judged was better preserved for the systems most directly responsible for maintaining communication and collecting the measurements no other instrument in any location can provide. The low-energy charged particle detector is projected to follow in 2026. Then, progressively, the remaining instruments and systems, not in a single catastrophic failure, but in a carefully managed series of deliberate deactivations, each one extending the life of the others by a few months, each one removing another layer of capability from a spacecraft that is already operating at the absolute minimum required to call itself operational. The current projection places Voyager 1's final threshold, the point at which the remaining power is insufficient to sustain even basic data transmission, at approximately 2036. Give or take a few years, depending on how efficiently the remaining power can be managed, and how many additional fault conditions require power-intensive recovery operations before then. 2036 is not a distant abstraction. It is roughly as far into the future as the year 2014 is in the past. A span of time that, at the current pace of technological change, will arrive before many of the engineers working on the spacecraft today have retired. When that threshold is crossed, and Voyager 1's last signal falls below the sensitivity of the Deep Space Network's antennas, humanity will lose something that currently has no replacement and no successor in development. The only operating scientific instrument in interstellar space, Voyager 2 crossed the heliopause in November of 2018, traveling in a different direction through a different region of the local interstellar medium, and is also still operational, also declining, also running on a fixed power budget that will reach 0 on a timeline similar to Voyager 1's. When both spacecraft go silent, our direct observational window into the interstellar medium will close. Not because the interstellar medium will have changed, not because the scientific questions will have been answered, but simply because the instruments capable of answering them will have run out of power in the most remote locations any human-made object has ever occupied. There are mission concept studies underway for a hypothetical interstellar probe spacecraft that could travel faster than the Voyagers by using a large solar sail or a gravitational assist from a close solar flyby, potentially reaching the heliopause within a decade of launch, rather than the 35 years it took Voyager 1. But concept studies and approved flying missions are separated by budget cycles, congressional appropriations, engineering development timelines, and launch schedules that make it extremely unlikely that any operational successor will be generating interstellar data before both Voyagers have gone silent. The gap in humanity's direct observational record of the space beyond the solar system will be real, and its length is measured in decades at minimum. More likely, in generations. Jamie Rankin, the deputy project scientist for the Voyager mission at Princeton, describes the situation in terms that are precise in their implications. Voyager 1 is traveling through regions that are completely unexplored, and when it stops, those regions will become unexplored again. Dark, unsampled, unmeasured, until another instrument reaches them. Kostas Dialinas, a space physicist who has published extensively on Voyager interstellar data, notes that it will take decades before another scientific mission provides the opportunity to pursue the novel research directions that Voyager has opened the plasma density gradient, the structure of the local interstellar medium, the dynamics of the heliosphere's outer boundary, questions that can only be addressed with instruments physically present in the interstellar medium, measuring the actual properties of the actual plasma, which is a data set that currently exists only because Voyager 1 exists. After 2036, the spacecraft will continue to travel regardless of whether it is transmitting, following its trajectory outward at 17 kilometers per second in the direction of the constellation Ophiuchus. In approximately 40,000 years, it will pass within 1.7 light-years of a dim red dwarf star in Ursa Minor, a flyby so distant that the star's gravity will barely perturb the spacecraft's trajectory. In several 100 million years, the differential gravitational field of the Milky Way itself, the galaxy pulling differently on objects at different distances from its center, will make the trajectory effectively unpredictable. The spacecraft will continue to exist for timescales that make the entire history of human civilization look like the thickness of a coat of paint on the wall of the universe, carrying its golden record and its map of pulsars and the memory of a graduate student's calculation and a woman's brainwaves toward a future that nobody currently alive will share. Andrewian wrote, in one of her reflections on the meaning of the Voyager mission, that she and everyone she knows will have been dust for more than 50,000 years before the spacecraft comes meaningfully close to another star, and that despite the near mathematical certainty that the golden record will travel forever without a recipient, the mission has taught us something worth knowing. The teaching has not come primarily from the discoveries, though the discoveries, the volcanoes of Io, the spokes of Saturn's rings, the plasma hum of interstellar space, the turbulent heliospheric boundary, are each individually significant enough to justify the mission's existence. The deeper teaching has come from the pattern of those discoveries, from the consistent finding, repeated at every scale and in every environment Voyager 1 has passed through, that the universe is more complex, more structured, and more resistant to clean theoretical description than our models predict from a safe distance. Every boundary it has crossed has turned out to be more diffuse and more layered than the models suggested. Every environment it has measured has turned out to have more internal structure than the models anticipated. Every world it has observed has turned out to contain dynamics that the models predicted were impossible. The universe, as Voyager 1 has encountered it, is always more than the model it is measured against, always carrying more information, always generating more complexity, always producing more phenomena that require new frameworks to describe. This is not a criticism of the models or of the scientists who built them. It is a statement about the relationship between theoretical knowledge and direct observation, about the irreplaceable value of actually going somewhere, as opposed to reasoning about what it must be like from a distance. The models of the outer solar system built before Voyager 1's departure were the best that human science could construct with the data available. They were built by brilliant people working with genuine rigor, and they were wrong in ways that could only be corrected by sending something to touch the actual environment and report back on what it found. What Voyager 1 has spent 47 years demonstrating, through every correction it has forced on every model it has encountered, is that the universe will always find ways to be more interesting than we expect it to be. That the reality at the edge of everything we can reach will always contain more structure, more dynamics, more complexity than the best available description of it from within the comfortable range of what we can observe without going there. And when Voyager 1 goes quiet, somewhere around 2036, it will go quiet, having demonstrated that principle more convincingly and across more environments than any instrument before it. The interstellar medium will still be humming at 2.6 kHz. The plasma density will still be higher than the models predicted. The boundary of the solar system will still be layered and turbulent, and located farther from the sun than we placed it in our equations. but no one on Earth will be able to hear any of it for a long time. The spacecraft will keep moving. The record player will keep spinning. In a metaphorical sense, carrying the brainwaves of a woman in love across a galaxy that has no particular interest in receiving them, but will hold on to them for longer than anything else humanity has ever made. Longer than the pyramids. Longer than any language still spoken. Longer than the sun in its current form. Because space is cold and dry and empty in exactly the ways that preserve metal and gold-plated copper indefinitely. And whatever Voyager 1 is, whatever it means, it will continue to be that thing long after the civilization that launched it has changed beyond any recognition we could map from here. In the meantime, right now, tonight, there is a machine moving through the space between the stars at 17 kilometers per second, faster than a rifle bullet, achingly slow by cosmic standards, so far from home that the word home barely applies to the star it came from, returning data on a power budget smaller than 2 light bulbs, running software that once remembered Jupiter and now remembers only how to keep the signal alive, built by people who are mostly gone, carrying a gold-plated record addressed to recipients who may not exist, having overturned a dozen certainties and opened a dozen questions that will take generations to answer, proving with every year of continued transmission that the most durable things humans build are the ones designed to do almost nothing and keep doing it, quietly and without complaint, across distances that reduce every other human achievement to a footnote. That machine is Voyager 1, and for a few more years, it is still talking,